In problem 5, we're given a polynomial function that can't be factored by parts, and it's not the sum or difference of two cubes. So we still need to factor it in order to find the roots. This is going to be one of the more important problems on the test. It's going to be asked in this way. The first thing that'll be asked is how many roots does it have? And the number of roots, real and imaginary roots, that it has is equal to its degree. And since this is a third degree polynomial, that means it's going to have 3 roots. The next step is to list the possible rational roots. And the rational root theorem says that if this polynomial does have any rational roots, it'll look like a fraction, where the numerator of the fraction is going to be a factor of the constant term. So in the numerator, we list the factors of 14, which would be plus or minus 1, plus or minus 2, plus or minus 7, and plus or minus 14. In the denominator of this fraction will be all of the factors of the leading coefficient. In this case, that leading coefficient is 1. So all the denominators are going to be plus or minus 1. That means all of my possibilities are nice whole numbers, plus or minus 1, 2, 7, and 14. In part C, we're asked to factor it completely. And then you'll see that there's this sort of diagram there. This is meant for us to try these possibilities using synthetic division. So we're going to have to list all the coefficients of our polynomial, which are 1, 4, -5, and -14. And then start trying factors. So I'll start at the beginning of my list with the positive and -1. First, bring down this 1, multiply and add. Multiply by 1, we get 1. When we add 4 and 1, it's 5. 1 times 5 is 5. When we add them, we get 0. 1 times 0 is 0, and when we add them, we get -14. That means that 1 is not going to be a root because it has a remainder. So we're going to try -1. Once again, bring down the 1. Multiply and add, multiply and add. So multiplying by -1, we get -1. 4 minus 1 is 3. -1 times 3 is -3. Adding those two, we get -8. -1 times -8 is +8. And when we add those two, we'll get -6. Once again, we have a remainder. So -1 is also not going to be a root. That means out of our list, positive and -1 just aren't going to work. So now let's try 2. Again, bring down the 1. 2 times 1 is 2. 4 plus 2 makes 6. 2 times 6, that's 12. -5 and 12 makes 7. And 2 times 7 is 14. -14 plus 14 makes 0. That's great. We finally got that remainder to equal 0. That means that we can rewrite f of x using these two pieces of information. First of all, f of x is going to have one factor that comes from this 2. This 2 is one of the roots, so the factor is x minus 2. Then, with the 1, 6, and 7, that's the remaining polynomial, where 7 is the constant term, 6 is 6x, and 1 is 1x squared. So the polynomial is x squared plus 6x plus 7. Now it looks like that x squared plus 6x plus 7 is factorable, and if it were, you should factor it. But the truth is, it's not. So we're not going to be able to factor it. So when we have to list those roots, we have to set each of those factors equal to 0. The first one being x minus 2, and the second one being x squared plus 6x plus 7. To solve x minus 2 equals 0, we just add 2 to each side, and there's one solution. For the other one, since it's not factorable, we're going to have to use the quadratic formula. So x equals -b plus or minus the square root of b squared minus 4ac all over 2a. And then we simplify. 36 minus 28 is 8. Simplifying that, square root of 8. The perfect square factor of 8 is 4. Square root of 4 is 2. So 8 is going to be 2 square root of 2. Then we divide each of those terms by that 2 to get negative 3 plus or minus square root of 2. And those are all three of our roots. 2 and negative 3 plus or minus square root of 2. I just want to go back and make it very clear for part C, when I ask for f of x to be factored completely, the answer is going to be this line right here, where we have the two factors that can't be factored anymore.